Hi everyone, I am Dr. G. Srinivasu, Associate Professor, Department of Mathematics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this present video, I would like to discuss the Green's theorem verification problems in vector integration. So we know that Green's theorem is a transformation between line integral and a double integral. So the statement of the theorem is, if C is any closed curve bounded by the region R, this is the C is the closed curve, and R is the region bounded by the closed curve C, and M and N are two functions which are defined on the region R and which are continuously differentiable functions, then integral over the closed curve C m dx plus n dy is equal to integral over the region R dou n by dou x minus dou m by dou y dx dy. This is the statement of the theorem. So m and n are functions of x and y which are having continuous partial derivatives, and the line integral over the closed curve, the circle indicates that closed curve C, m dx plus m dy is equal to double integral over the region R. This is n partial derivative with respect to x. This is m partial derivative with respect to y dx dy. So clearly it is a relation between the line integral and a double integral. So how to verify the Green's theorem? So verification problem means you have to show that the left hand side line integral and right hand side double integral, if both are same, then we can say that the Green's theorem is verified. And in Green's theorem problems, you may ask to evaluate the line integral if the information given as a double integral. So if the double integral is given, you need to calculate the line integral. If line integral information given, you need to calculate the double integral. So in this, we have two types of problems. One is verification type problems and other one is finding of the line integral or the double integral when the other integral given in the given problem. So now go to the first problem. Verify Green's theorem in a plane for the integral closed curve C xy plus y square dx plus x square dy, where C is the region bounded by the line y is equal to x and y is equal to x square. Here, first we have to find the region and the closed curve. Here the two curves, here the given curves. Here the given curves are y is equal to x and y is equal to x square. So what is y is equal to x? It is a straight line passing through 0, 0. Y is equal to mx format. This is x square is equal to 4ay. It is looking like x square is equal to 4ay. It is a parabola symmetrical about y-axis. So first identify the curves, then I can draw the curves. This is x-axis, this is y-axis, and what it line indicates, this is y is equal to x line, y is equal to mx line, and this is horizon 0, 0. And the other curve is given as the parabola whose vertex is 0, 0, and it is x square is equal to y. So here the region is bounded by the straight line and the parabola. That means this is the curve. The curve is, the closed curve is this one. This is the closed curve. This is O and this is A and OA, So in this way you can identify. So here the intersection point of the two curves, y is equal to x is one curve and y is equal to x square is other curve. On solving these two, you can get the intersection points. On solving, I can write x is equal to x square. Left side are both are same, y, x square is equal to x, or x square minus x is equal to 0, or x into x minus 1 is equal to 0. That means what? X takes the values 0, 1, Then when x0, y also 0. When x1, y also 1. When x1, y1, when x0, y0. This is 0, 0. And other point is 1, 1. This is already known point. Origin 0, 0. You know that? Here we got through the intersection point 0, 0, 1 intersection point, and 1, 1 is the other intersection point. Now we have to evaluate the line integral along this curve. That means along OA and along AB. So first one I want to see the line integral. The line integral along OA. What is along OA? Here it is along OA. So what is the curve? This is the curve y is equal to x square. This is y is equal to x square. Here the curve is here. The equation of OA is y is equal to x square. Then what is the dy? 2x dx. And here what is the function? Integral along OA, already given mdx plus ndy, xy plus y square dx, plus already in the problem given the function mdx plus ndy. Integral along OA mdx plus ndy. I am going to calculate. So along the curve OA means it is along y is equal to x square. When y is x square, dy is equal to 2x dx. The entire function I am going to change in the terms of x square, x terms, x already there. Y means x square. That means what? X into x square. The first term will become x cube. Next, on place of y I am replacing x square whole square, x power 4 dx as it is. To evaluate the line integral, I am changing all the terms in terms of one variable, either in y or in x. Similarly, x square, what is the dy? 2x dx. dy is 2x dx. Because we are using the variable x, we have to write the limits for x. X varies from 0 to 1. Here x varies from 0 to 1. Therefore, 0 to 1. Now on integrating, what we will get? This is x cube plus x power 4, 0 to 1, plus what is this term? 2x cube of dx. Or it is x power 4 plus 3x cube of dx between 0 and 1. It is what? X power 5 by 5 plus 3 into x power 4 by 4 between 0 and 1. So substituting the limit, what will you get? 1 by 5 plus 3 by 4. Lower limit 0. Here also lower limit 0. So the LCM 20. 5 4s are 20. 4 1s are 4. 15. That is equal to 19 by 20. 19 by 20 is the line integral value along OA. Similarly, along AO. What is the equation of AO here? AO means this is y is equal to x. The equation is y is equal to x. The equation of AO is y is equal to x. Then what it is? dy is equal to dx. So now I'm changing all the terms in terms of x or y, xy, that is x square, y square means x square, of dy means dx, dx is same as dx, x square same as x square of dx, x limit means 0 to 1, as like in the previous case. No. So here x limit is 1 to 0, here x limit is 1 to 0. Here we have to consider the direction also. X limit varies from 1 to 0. That is also important. Direction also important. 1 to 0. So it is 2x square plus x square. 3x square dx between 1 and 0. Or 3x cube by 3 between 1 and 0. Or 0 minus 1, that is equal to minus 1. Here it is 19 by 20. Here it is minus 1. Therefore, the line integral along the curve C m dx plus n dy is equal to, one is 19 by 20, second one is minus 1. Along OA and along AO. So it is equal to 20 LCM, 19 minus 20, that is equal to minus 1 by 20 is the first evaluation, line integral. So we have evaluated this one. What is the theorem integral? So first I read the theorem statement also. Here the statement is integral. What is the statement? Integral m dx plus n dy over the closed curve C is equal to double integral dou n by dou x minus dou m by dou y dx dy over the region R. So this is evaluated already. This value is, already we have seen that value is minus 1 by 20. This value we have reached minus 1 by 20. Now we have to calculate this one. So how to calculate the region? Already I have seen the figure. This is the straight line y is equal to x. This is x square is equal to y parabola. So the intersection point 1 comma 1, this is 0 comma 0. So on considering the region inside considering the strip inside the region, the strip parallel to x-axis, that is y is equal to x square to y is equal to x. So I have to evaluate the double integral. Double integral means we have to consider the strip inside the region. This is the region, capital R. On considering the strip parallel to y-axis, the limit for y will be variable limit. That limit is from x square to x. So double integral over R dou n by dou x minus dou m by dou y dx dy is equal to, now first I want to find what is m here. Here I will m is equal to xy plus y square. And what is n? N is equal to x square. What is dou n by dou x? X square derivative. Dou n by dou x is equal to 2x. And what is dou m by dou y? Dou m by dou y, the partial derivative of m with respect to y. Dou m by dou y, x plus 2y. y1, x as it is, constant when you are differentiating partially with respect to y, y will become 1, x into 1 plus 2y. So I will write x plus 2y, that is x plus y square derivative 2y. Now on taking the double integral, dou n by dou x 2x minus x minus 2y of dx dy over the region R. For what I can write? This is x minus 2y, and first integration is carried out with respect to y, because y limit is a variable limit from x square to x, and x limit is a constant limit from 0 to 1. So first integration is carried out with respect to y first, and then with respect to x. So integral 0 to 1 x limit. First y to j, integration means it is along with the strip. Along strip means the limits will become x square to x. That limits already written in the first integral, and the second integral is constant limit from 0 to 1. So now on integrating with respect to y, x integration xy, 2y integration 2y square by 2 between x square and x of dx. So this is integral 0 to 1 x into y, that means x into x, y plus x, on replacing x square, 2 to cancel, minus x square, and lower limit minus x cube, minus of minus plus y, instead of y I am writing x square, so it is x power 4 of dx. So this and this gets cancelled, 0 to 1 x power 4 minus x cube of dx. So what is the integration? X power 5 by 5 minus x power 4 by 4 between 0 and 1, or 1 by 5 minus 1 by 4, and lower limits are zeros. So LCM 20, 5 fours 20, 4 ones are 4, 4 fives are 20, 5 ones are 5, that is minus 1 by 20, and this is the right hand side result, minus 1 by 20. Already we have reached the left hand side result minus 1 by 20, and the right hand side result also minus 1 by 20. So the Green's theorem verified, because integral over the closed curve C, m dx plus n dy is equal to double integral over r dou n by dou x minus dou m by dou y dx into dy. So both results are LHS, RHS, both having the values minus 1 by 20. So the Green's theorem is verified. The Green's theorem is verified. So that is the method of doing the verification problem. And I will stop this session by doing this small problem. Evaluate by Green's theorem in a plane for integral over the closed curve C, y minus sin x dx plus cos x of dy. So m dx plus n dy, integral over the closed curve C, where curve is given by the triangle. The given curve is the triangle enclosed by the lines. Y is equal to 0, that means x-axis. One of the lines or boundaries are y is equal to 0, that is x-axis. X is equal to pi by 2. X is equal to pi by 2 means that is a line passing through pi by 2 comma 0. This is the line x is equal to pi by 2. This is y-axis. Y-axis means x is equal to 0. And what is the other line given? This is not required here. And other line given, y is equal to 2 by pi into x. Y is equal to 2 by pi x means it is a line passing through origin. Y is equal to 2x by pi. The boundaries are the straight line, y is equal to 0 x-axis, straight line x is equal to pi by 2, and y is equal to 2x by 5. So this is the region of integration. This is the region, or capital R is the region bounded by the three lines, and the curve C is bounded by the x-axis, x is equal to pi by 2 line, and y is equal to 2x by pi line. But here we no need to verify this theorem. Here we have to evaluate the Green's theorem in a plane for the line integral where C is the triangle enclosed by these lines. So we need not to evaluate the line integral along this and along this, along this. So it is a lengthy procedure. You have to evaluate like this, like this, like this. You have to add all these three. It is a lengthy one. So instead of that, we can use the double integral. What is the double integral? So by Green's theorem, the statement integral over the C, m dx plus n dy is equal to double integral over r dou n by dou x minus dou n by dou y dx dy. So instead of using the line integral, I am using double integral by Green's theorem. That is integral over r dou n by dou x. It is m and it is n. N is equal to cos x. What is dou n by dou x? Cos x derivative minus sin x. Cos x derivative minus sin x plus. So here it is minus dou n by dou x minus dou m by dou y. So the partial derivative of m with respect to y, that is 1 only, this will be 0 because we are differentiating partially with respect to y. So x terms treat as constants, it is 0 of dx into dy, where r is the region bounded by the three lines. Now to find the limits of integration, minus take outside, 1 plus sin x, and here first dy dx. So what is the y limit? We have to consider a strip inside the region. To find the limits of the integration, we should consider the strip inside the region either parallel to y-axis or parallel to x-axis. If we take parallel to y-axis, y limit will be variable limit. If we take parallel to x-axis, then the x limit will be x variable limit. So here y0 to and y is equal to 2x by pi. So the lower edge of the strip is on x-axis, that is y0. The upper edge of the strip is on the line y is equal to 2 by pi into x. So y is equal to x by pi. And what is the limit x varies from? X, this is 0, 0. And up to this point we have to vary. That is 0 to pi by 2 is the x limit. Up to this, I hope it is clear. 0 to pi by 2 minus, on integrating with respect to y. So y plus y sin x between 0 and 2x by pi of dx. So on replacing minus 0 to pi by 2. So y for 2x by pi, upper limit 2x by pi plus 2x by pi of sin x, lower limit y0, 0 of dx. Now integrate. On integrating UV form. On integrate integral, first one 2 by pi x square by 2. Now we will write minus, so I will write here minus integral 0 to 1 limit 2x by pi plus 2x by pi sin x of dx. 2x by pi plus 2x by pi sin x of dx. And before that it is minus sign, already it is there. So on integrating, what we will get? Minus integral 2 by pi into, so x integration, x square by 2. Now again 2 by pi constant, integral 0 to 1 x into sin x into dx. And this is limit 0 to 1. So minus of first one 1 by pi, lower limit 0. 1 by pi, lower limit x plus the 0 as it is entire 0 plus 2 by pi into, here we have to use integral u dv. Here u is take x and dv is equal to sin x dx. Then u dash is equal to 1 and v is equal to minus cos x dx. Integral sin x means minus cos x. So what is the formula? uv minus integral u dash u into uv minus integral u dash into v. That means what? Minus plus integral cos x dx. That means the sin x will get the limits 0 to 1. U into v minus integral u dash into v. So minus of 1 by pi plus 2 by pi. Here x, instead of x I put 1 minus cos 1 plus sin 1 and lower limit 0, 0. So this is minus of 1 by pi, or you can take outside 1 by pi, that is 1 plus 2 into minus cos 1 plus sin 1. That is the required solution, or 1 by pi minus sin, or sin 1 minus 1 minus 2 into cos 1 plus 2 sin 1 is the required solution of the given problem. So here we have evaluated the problem using Green's theorem, and here we have used the double integral instead of line integral. So these problems has been considered from the IARE question bank, differential equations in vector calculus BT23, published by IARE. So with these a few problems discussion, I conclude my session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.